Radio communication depends upon electromagnetic waves radiated through space from an antenna. These waves carry messages over great distances, maintaining air and ground communications. To understand the fundamental principles of the antenna on either fixed or aircraft installations, it is first necessary to have some conception of how radio waves are generated and how they behave. If we hold a compass near a wire through which a direct current of electricity is passing, the needle will be deflected. A magnetic field exists around the wire as long as the current continues to flow. Lines of force are created around a conductor and remain while current flows. These lines of force collapse whenever the flow of current stops. The direction of these lines of force, making up the magnetic field, changes whenever the direction of current flow is changed. If we charge a glass rod by friction, it will attract objects from a distance. This is static electricity. Around the charged object, lines of force extend out at right angles from the surface. In this case, the field is not magnetic. It is a dielectric field. This field remains around the object as long as it remains charged. Thus we see that electricity flowing as a direct current generates a magnetic field, while around a charged object in which there is no flow of current, there is a dielectric field, sometimes called an electrostatic field. In a hookup consisting of a battery, switch, and condenser, maximum current flows the instant the switch is closed, resulting in the creation of a magnetic field at the instant of closing the circuit. This magnetic field remains around the conductor and condenser as long as current flows. When the plates of the condenser are fully charged, current ceases to flow. The magnetic field around the condenser and conductors collapses as current diminishes. The condenser is then a charged object, and a dielectric field is built up around it as the charge accumulates. If the battery is reversed, the dielectric field collapses. The energy returns to the circuit and then builds up in the opposite direction. Rapid changes in polarity in the circuit result in rapidly changing dielectric and magnetic fields. If the condenser plates in such a circuit are moved apart, the dielectric and magnetic fields move out to greater and greater distances. When the polarity of the battery is reversed, the field collapses and is built up in the opposite direction. Both fields are projected out and return at the speed of light, 186,300 miles per second. Very rapid changes in polarity are possible if a high-frequency generator is used. When the polarity of the system is suddenly changed, the field which has been built up starts to return to the circuit. However, the reversal in polarity starts another electromagnetic field moving outward. This new field, or wave of energy, meets the first one before it has had time to return to its source. The returning energy in each case, meeting the oncoming new field, is forced out as an electromagnetic wave. When each new field starts to collapse, it meets another surge of energy and is driven out as another wave. With a radio tube as oscillator, a rapid continuous series of waves results. These are radio waves. Radio waves move in all directions from the radiating source or antenna, traveling at the speed of light. All radio waves move at the same velocity. Low-frequency transmission results in long wavelengths. The more rapidly the waves follow each other, the higher the frequency. The higher the frequency, the shorter the wavelength. Radio waves tend to travel in a straight line, much as does light. They may be reflected or refracted. An example of reflection is seen near an antenna, where the earth is the reflecting medium. The refracting media are layers of ionized gas in a region from 50 to 300 miles above the earth. In this region, known as the ionosphere, the layers of ionized atmosphere so bend radio waves that they act as if they had been reflected. An upper angle or sky wave may thus be returned to the earth at a great distance, where it may be heard with good volume. The sky wave returning from the ionosphere may be reflected by the earth, going into the upper atmosphere again, where it is refracted back toward the earth a second time. This refraction and reflection may be repeated several times, so that a message may often be heard thousands of miles from the transmitting station. The higher frequencies are refracted the least, some extremely short waves failing to return to the earth at all. This low refractive index of the medium-high frequencies makes them desirable for long-distance communication. Antenna installations are often adapted to the particular characteristics of these high frequencies. That portion of the antenna's radiation traveling near the surface of the earth is called the ground wave. The polarization of this ground wave changes as it travels, tending to lean forward. The ground wave loses energy rapidly. Accordingly, it cannot be used for long-distance communication. The ground wave of the lower frequencies travels farther than do the higher frequencies. Extremely high frequencies act almost as does light, failing to follow the Earth's curvature or to go around obstacles. In many cases, a silent strip exists between the point where the sky wave returns to Earth and where the ground wave has become too attenuated or too weak to be detected. This is known as the skip distance, or zone of silence. There may be more than one skip distance when the wave is reflected into the sky from where it is returned and reflected again. For example, a powerful station in Cincinnati may not be heard in St. Louis. Yet beyond a zone of silence, it comes in clearly at Kansas City. Beyond a second zone of silence, the station may again be heard in Denver. Fading may be due to changes in the ionosphere level. This shifts the position of the returned sky wave. The signal is heard when it is returned to the receiving station and fades out when it misses the station. Fading is often due to interference effects between the ground wave and the returned sky wave. The two waves strengthen each other when in phase. When out of phase, they weaken or destroy the signal altogether. Distortion as well as fading may be due to this interference effect between waves, both of which are from the same station. Space about is filled with unseen waves, sent from many antennae. Out of the maze, an efficient receiver and antenna will select but one, translating it into an intelligible message.
Great tower to Fermi, 1258.